Now, question 8. Reconciliation question. Looks straightforward enough, but you have to watch out for the inner workings of the reconciliation. What does it say? It falls by 20%. The same amount of food goes in. It falls by 25%, and then it gets fed again. Now that makes a zigzag pattern. It says it starts with 1. Starts with 1 gram. That 1 gram over a period of time will fall by 25%, and then go up by another 1, and then fall again, and then go up again. These are the values that you calculate at the end of your reconciliation, but in between it falls. It forms a sawtooth pattern. There's a maximum and a minimum. And where this question says bioforce is only effective when there's continuously more than 2, that means you don't want it to fall below 2. So it's not the maximums you want to exceed 2, it's the minimums that need to exceed 2. But you can always tell the difference between the maximum and the minimum is always 1, in this case, if it's 1 that's been added. So when you use your reconciliation and it gives you these values, which then produce a limit later on, if it does produce a limit, then you know that it's not it's a dynamic, not a static limit. Whatever the limit is, it's always going to fall and then rise again. It's just because it falls and rises by the same amount that it reaches a limit. There's always a maximum and a minimum, but it's easy to tell the difference between the maximum and minimum, just the amount it rises. So for this question, it says initially there's 1. Now I'll have to use my calculator. So that means I'll just put 1 in. Put 1 equals, that's stored at an answer. So I'll just call that U0. Sometimes it's a bit ambiguous about which bits gets counted, but we'll say so that after 1 week it'll be this. So you do this times 0.75 plus 1 equals, maybe I should write it down now. So after 1 week it will be times 0.75 because it falls by 25%, then you add 1 back on, so you've now got 1.75. So you started at 1 and it's gone up to 1.75. But before that it had obviously fallen by 1, it had fallen to 0.75. There you go, U2. U2 will be same calculation, I don't need to repeat it, I'll just press the button. 2.3, 125, 2.3, etc. And then you think, bingo, that's it. 3 feeds does it. No, it doesn't. That might be above 2, that's this part here, 2.3. But it's going to fall again. 2.3 had fallen before that. So we'll have to work out U3. U3, press the button again. I've got 2.73 and so on. So it fell and now went up to 2.73. That's still no use because before 2.73 it must have fallen down to 1.72. So it still hadn't hit the magic figure of 2. I'll just check what the next one is. U4 then. U4 is going to be 3.05. So the next one's 3.05. And that one's fine because it must have fallen to 2.05 before it. So the correct answer to this question, depending what they mean by weekly feeds, is it took 4 feeds. Because at the end of the 4th feed, when it ran out over the week, it was still above 2. So the answer to this really is it takes 4 feeds. Now whether the question means, it's a bit ambiguous, how many feeds after the initial one, or whether that includes the initial one, but it took 4 feeds altogether, I'll say. It took 4 feeds altogether to stay above 2 grams. That's going to be my answer to it. You have to remember this business about it going up and down in between. Part B. Write down a reconciliation for the amount of plant food in the tree immediately after feeding. Well, that makes it easy. It's just what we were doing then. So UN plus 1 was 0.75 because it lost 25% of UN plus 1 because it wants the amount after you've added the 1. If you'd wanted the reconciliation before the feeding, then that would have been this way then. So that means before the feeding, you hadn't added the 1, so before the previous feeding, you'd have just added the 1, so it'd actually be 0.75 times that. It'd be 0.75 UN plus 0.75, which looks totally different. But all you're doing is you're going through this sawtooth, it's like a shift. All that reconciliation would give you, if you wanted the amount before the feeding, would be the bottom parts. This would be the reconciliation that at the end of the result would give you the minimum values, whereas this is a reconciliation after the feeding that gives you the maximum values. They're both really the same thing, there's just a slight phase between them. But that's that part anyway, that was just the 1 mark. And then 2. If you continued to do this, would it exceed 5? Now again, you have to watch your limits. At the limit's dynamic. The limit to a reconciliation doesn't look like that. You know, if something happens over time, it's a sawtooth. It falls, then it rises, it falls, then it rises, it falls over time, rises with a feed. It looks like this. There's a maximum and a minimum. You have to consider that. The reconciliation gives you the maximums, but you know the minimums are whatever this is down below it. So if it says it must never fall below a certain value, it's not the maximums you look at, it's the minimums you're looking at. If it says it must never rise above a certain value, it's the maximums you'll be looking at. So for this one, what does it say? Is it safe to continue feeding at this rate indefinitely? Well, first of all, does it have a limit? Well, you'd have to make this statement. Since that multiplying ratio, since 0.75 is a proper fraction, you can either put greater than -1, less than 1, or since its absolute value is less than 1, that means a limit exists. That means a limit exists. And that limit will be given by the formula. I'll have to go up to the top, this is all getting a bit messy. And that limit will be, you could just use the formula here, b over 1 minus a. So that's 1 over 1 minus 0.75. Or if you like 1 over 0.25, I'll put it down anyway. That's a quarter, so that must be 4. So that's 4 units, grams. So there's a limit of 4 grams. Now that's the upper limit. It says it mustn't exceed 5. Well, it's nowhere near it. So the question was again, is it safe? Yes. So you have to say yes. Yes, it is safe as the limit is 4 grams, which is less than the 5 gram level. Well, you can be more exact and say, yes, it's safe as the maximum limit is 4 grams, because it goes between 4 and 3 all the time, which is less than the 5 grams level that would have been dangerous. Number 10, optimisation question. First part, derive this formula for very few marks, and then the second part, use it to find the answer for an inflated number of marks, usually because you've already got marks for finding turning points before. Still, the first part. Hemispherical top, cylindrical side, so there's a circular base, even tells you the area of the hemisphere, 2 pi r, so that area is going to be 2 pi r squared. The volume of a hemisphere, the surface area of a sphere, 4 pi r squared. The surface area of that cylinder, well, that would open out to a rectangle whose length would be the circumference, pi d, 2 pi r. So its area is going to be length times breadth, 2 pi r times h. Base, circle, pi r squared. Which means the area is going to be given by, now it says AR here, but I've got h's. So strictly speaking, I should say A is the function expressed in terms of r and h, would be the sum of all of those. I've got 2 pi r squared, 2 pi r h, plus another pi r squared. I'll stick over here. So that's 3 pi r squared plus 2 pi r h. Now I know I could take it more factors, but I don't want this h because it says it's just going to be one variable. So there must be more information somewhere. Something that'll let me change h's into r's, and it is. The volume of the cylinder is 400. Volume of a cylinder, pi r squared h. So pi r squared h is 400, and immediately you get from that h is 400 over pi r squared. So you can substitute that in there. So it's going to be 3 pi r squared plus 2 pi r times 400 over pi r squared. And that was, if you like, from 1. And then tidy that up. 3 pi r squared, the pi cancels, the r cancels, so that's going to be 800. So plus 800 over r, and now there's only one variable, so a as a function of r is equal to that. So part B, find the value of r which ensures the surface area is minimised. Right, well that means I want to find, because this function here will either keep on increasing forever or decreasing forever and not have any optimum values, unless of course there's a limit. There's some interval which contains r, and then the limits would be either at the minimum or the maximum value of r. it would only have an optimum if somewhere between them it took a turn. So I'm looking for stationary points. I want to find when, I could just write it as A dash star. I want to find if A dash star is ever equal to 0. Well, differentiate it. Well, before I can differentiate it, that's a bit hasty, I'll need to change that. 3 pi r squared plus 800, take the r up. I need everything in index form to differentiate r to the -1, because it's the indices that you work on. Right, now I can differentiate it. A dash star is going to be 6 pi r minus 800 r to the -2. What does that mean? 6 pi r minus 800 over r squared. So you'll have an optimum value to the function if that derivative is ever equal to 0. If 6 pi r minus 800 over r squared ever equals 0. Well, given that, we're not going to consider the case r equal to 0. So r's not going to be 0. I could just multiply throughout by r squared. I won't actually be multiplying by zeros. So get rid of the, or you could just think, take that part over there, but you're still going to multiply by r squared. So multiplying everything by r squared gives me this. 6 pi r cubed minus 800 equals 0. Now there's only one mention of r, so you can just take everything across and solve it. So 6 pi r cubed is 800. R cubed is going to be 800 over 6 pi. So r is going to be, unfortunately, the cube root of 800 over 6 pi. Now, those aren't perfect cubes, so there's not a lot you can do about that, apart from just get your calculator. Now, click. So we'll say r equals 3.5, and was that centimetres, was that metres, or was it reading centimetres? However, that doesn't demonstrate that it actually forms a minimum there. So that means I'd have to make up a quick table. I could put the table just up here. You could do the second derivative, but that's a bit nasty. First derivative's not got a lot going for it either. But I know that at 3.5, then the derivative was 0. And so I could just pick some values just before and just after it. So you could pick out something like 1. That should be quite easy to work out. I can go up at 10, that makes nice numbers to put in for this. So at 1, I've got just 6 pi minus 800, that's negative. And at 10, that's going to be 60 pi, but that's only going to be minus a tiny bit, so that's going to be positive, which means it looks like this. So it is minimum. So area is minimised at r equals 3.5. That would do it. And so question 11, logs, experimental data type 1. Now what's the first part? First part for 3 marks anyway. The variables x and y are connected, it's suspected that they would be some sort of power form, some exponential form like this. Show that there's a linear relationship. In other words, if you were to draw the graph between these two things, if you were to draw the graph of log y and x, as that's the axis and that's that axis, it would be a straight line of some sort. Well, start breaking it apart using logs then. So take logs of both sides. So you've got ln, it says log base here, just write ln. ln y would be the same as ln of a e to the bx. Splitting that apart, it's the sum of the two parts. So ln of a and ln of e to the bx. So I've got ln y equals ln a plus, now that part, that will just come to bx, because that says what power of e, log n e says what power of e is e to the power bx, it's obviously bx. Or you could split that up by thinking, take that to the front, extract the power, and then you've got log n e of e is 1, still giving you bx, either way it's bx. And that's in the form of a linear relationship. I've got log n of y equals bx plus ln of a. That's in the form of y equals mx plus c, which is in a linear form, where y equals ln and x is just x. So that would be the first, maybe we should have said in form. So it's in that form. Finish that off, where y equals ln of y and x is just equal to x. Part B, experimental data now. There's 4 sets of data. There's no graph to indicate how close any of these are to the line of best fit, so we'll just take the first 2, so that's what I put down there. Now there are several ways to work out B and A. 2 of them are by forming simultaneous equations, and the third way would be by just considering what that graph would have looked like, plotting ln y against x. It'd be some sort of straight line, where B would be the gradient of that straight line, the gradient being the difference of the vertical component over the difference in x, so difference in ln y. So you could do that. You could work out B by saying difference in, not the difference in y, but the difference in ln y. We'll just do it that way first. Right, so B is going to be the gradient. I'll put that in words. It's going to be the gradient, which means the difference in the vertical variable. So it's the difference in ln y over the difference in x. So that would be ln 72631 minus ln 21876 over the difference in x, 3.5 minus 3.1. And then you could just type that in, or you could say, well, ln 72 etc minus ln 21 etc is the same as the ln of the 72 etc over the 21, and then do a single logarithm. But I don't know if there's any advances to do that, because you're going to have to use logarithms anyway. So it's just a case of typing that lot in. So it's top in brackets, bottom in brackets, click to click, and it comes to 3.0000 blah blah. Well, there's a 4 actually, which means fairly confident that B equals 3. Then, knowing that B equals 3, you could put it back into that equation. So you've got ln y equals 3x plus ln a. And then again, put in a pair of figures. We may as well use that first one. So you've got ln 21876 is 3 times 3.1 plus ln a. So ln a is going to be that thing minus that thing. I'll just put that down. So again, so ln a equals that, which means a will be inverse of log base a is e to the power 0.6931. Now we've got all that stored under the answer, so I just need to do e to the answer. So that'll be a so a equals 2. So that was just using that equation there. Thinking of the graph, right? Now another way would just be forgetting about the actual geometry of it, of the graph and so on, just treating it as you've got a pair of values, there's 2 things to find, so 2 simultaneous equations, although it's completely equivalent to what you just did. You'll see that anyway. So that would be, you would take 2 points, well, we'll call them 1 and 2. So if you took point 1 and fed that in, you would have this. You'd have ln 21876 is b times, so 3.1b, plus ln a. There's one equation. Could write it the other way around, I'll just leave it like that. That's one equation. Taking point 2, you've got ln 72631 equals 3.5b plus ln a. There's a second equation. Then treating them as simultaneous equations, you could subtract them to remove a. Then there's only b's in it. So you would have this. So if you did 2, because that's the larger number, take away 1, well, if you had 2 take away 1, what you're going to have is ln, just as before, you're going to have ln 72631 minus ln 21876. That side's going to be 3.5 minus 3.1 lots of b. 3.5 minus 3.1, and they're both of b. So to get b, you're going to be dividing by 3.5 minus 3.1, and that's just what you did before. So doing it as simultaneous equations was exactly the same calculation as working out the gradient. But you could do that, subtract those 3 things, and then again you would get b equal to 3. And then once you had b equals to 3, you would substitute it in, and that would just be identical to what you had before. So that would be the second way. Simultaneous equations. Simultaneous equations using that linear form that they required you to turn it into in part A. but part B didn't say hence, so another way would be this. Go back to the original form, which was y equals ae to the bx, and just substitute them straight into that. But again, you'll notice the exact same calculations will rear up once more. So substitute them in. If I take point 1, then I've got this equation. For point 1, I've got ae, I'm just going to write it the other way around, ae to the 3.1 b equals 21876. If I take point 2, I've got ae to the 3.5 b equals 72631. That's just directly putting the y and the x into that original equation. And then I've got a pair of equations, I'll just refer to them as those 1s and 2s. Pair of simultaneous equations, there's different techniques for solving them. You've met this before with the wave function. One way of getting these would be to divide the two sides. So dividing the two sides, if I do it as 2 divided by 1, will give me e to the 3.5b over e to the 3.1b is 72631 divided by 21876. It's coming back again. Dividing those, same base, subtract the powers, e to the 0.4b, there we go, equals whatever that quotient is, I'll just put ditto. And finally, well not finally, 0.4b is going to be opposite of e to the power, log base e, will be ln, or you can write log base e if you like, of that quotient. Exact same in the last calculation. Which means that b would be, since I'm running out of room, divided by 0.4, exactly the same calculation as before in any of the other 3 ways, which gave you that same value, 3 point, etc., etc. forever. Only this time you'd be substituting it back into this form. So now you've got y equals ae to the 3x. And then you'd put any figures in you liked. So you'd have ae to the 3 times 3.1 equals 21876. So a would just be 21876 divided by e to the power 9.3. Now you didn't do that calculation before, so we'll just quickly check that. Exactly the same as before. So that would be the various ways of doing question 11. You just have to study through the different ways to decide which way you'd prefer if it wasn't indicated in the question. And that's the paper finished.